Next topic, wood lateral systems. Moving on to the next topic is wood lateral systems. We'll start with foundation anchor bolts. If you're using some post-installed anchors, verify with the approved drawings and the ICC approval reports for the minimum edge distances in both the wood and the surface that the bolt goes into, whether it's concrete or masonry. These pictures show improper edge and end distances. The picture on the left with loading perpendicular to the wall. For an exterior wall, you've got wind loads. You need an edge distance to the side of the lumber of 4 bolt diameters. You'll need that on both sides of the bolt because the wind load could be inward or outward. Picture on the right, you'd need to have 7 bolt diameters to the end of the lumber for along the length of it. That would also apply where you have notches, holes for conduit, etc. This picture shows an inadequate edge distance for your anchor bolt. This picture is a reminder that to verify the required anchor bolt embedment with the approved drawings. For section 2301.1.4, item number 3, it says that the exception in SDPWS section 43643 is not allowed. The section of the SDPWS is to require a 3x3 by 0.229 plate washer extending to within a ½ inch of the edge of the sill plate on the sheathing side of any shear wall. So you can't ever use the exception. The other item is a standard cut washer is also required when the plate has a slotted hole. Sometimes they'll have a slotted hole as shown so that you can slide the plate closer to the shear wall. If you've got a double-sided shear wall with a wide plate, typically the solution is to provide an anchor bolt with the plate within the ½ inch staggered on each side of the shear wall. So if you've got a big 10-inch wide plate, you'll have 2 rows of anchor bolts. Every other anchor bolt will be on the other side of the shear wall for a double-sided wall. If you just have single-sided walls with wider plates, 2x8 plates, for example, usually you'll have to have a larger plate than a 3x3 to get within ½ inch. You'll have to make some custom plates to get you that wide of a sill plate for the max ½ inch spacing. We have a few slides. This shows some split sill plates, obviously not acceptable. This picture shows a splice in the sill plate, and the contractor didn't put an additional anchor bolt in so that he would have an anchor bolt near the end of both pieces of the sill plates. Usually it's 9 to 12 inches or so maximum away from the end. Of course, 7 diameter minimum from the end. This is a picture of a undersized washer with an oversized holes, and the washer is pulled through the post and loaded. This is a picture showing a gap between the nut and the hold down. All bolts must be tightened or retightened before covering with sheathing. Upper levels are really likely to experience this with the wood shrinkage through the floor level, especially with sawn lumber. May not be as much when you have TGIs or laminated wood, manufactured wood. This is the picture of a hold down where they had to countersink the bolts because the hold down stud was too close to the end of the wall. A countersink bolt reduces both the strength of the hold down, the stud, and the bolt shear capacity. This would need to be verified and accepted by the engineer of record. If you see a hold down in the middle of a shear wall, it should raise a red flag. This particular one, there's a hold down at the top of the post that could be a drag tie from a level above. You'd also want to verify plywood edge nailing if the hold down is required per the drawings. There's a whole number of things that appear to be wrong in this picture. You've got hold down anchors that appear to be in the wrong location and bent over. Far right, you've got a 2x trimmer that was ripped down probably to a 1x because of the lack of distance to the end of the wall. The trimmer post right next to the hold down post on the right stopped short so that bearing load doesn't get properly transferred down to the sill plate. The sill plate on the bottom right there was plain, needs to be treated. You've got a couple of king studs on the left side of the hold down post that don't go full height. So a whole number of things to talk to the engineer about on that one. These pictures show a couple of different shear wall failures. On the left, you got a standard cut washer and the plate split. Not a very good behavior of that shear wall. On the right, you've got the larger plate washer that goes near the edge of the shear wall. You've got pull through and pull out of the nails and bending of the nails. That's a much more ductile and higher capacity failure mode than a sill plate failure. This is a good view to go through the shear wall requirements. On the far left, the vertical edge, you'll have edge nailing, boundary nailing. That nailing should be onto the hold down post. On the right side of the shear wall, which is next to the opening, that vertical red line, that would be your edge boundary nailing of the right boundary of the shear wall. That gets edge nailing for the full height of the hold down post. At the bottom of the shear wall is the sill plate. You'll have edge nailing there. At the top of the wall, if this is a high roof at an entry area and the roof beyond is a little lower, you would want edge nailing along the line of the low roof that's beyond. That should go along the length of the shear wall and across the opening as well. Edge nailing would also apply to the edges of all the sheets. Blocking is required in all shear walls, so all edges must be blocked and nailed. The field nailing would apply to the stud nailing in the middle of the sheet. Often you'll have straps at the top and bottom of the opening that'll extend left into the shear wall. That strap would also require blocking in the framing so that you can have nailing for the strap. The openings in the shear wall that aren't shown on the drawings, quite often you might have a large duct from the mechanical plans. The structural engineer missed it. If there's a large opening that's not shown on the structural drawings, you should contact the engineer of record, verify that he's considered that opening. For this slide, blow up of that top left picture, it's typical shear transfer details that are what you're going to see on plans, but on the top left picture, it shows the roof diaphragm coming into a shear wall. If it's an interior shear wall, usually you should see 2 rows of boundary nailing because there's a diaphragm on the left and a diaphragm on the right of the shear wall. It's usually considered a separate diaphragm on each side, and so you'll need 2 rows. At the top of this picture, you can see the typical shear transfer blocking that you'd expect through the joist. So the diaphragm nailing will be into the top of that blocking, and that blocking will then be connected to the double top plates to transfer the shear from the roof down to the wall. This picture shows a notched opening in the plywood panel. It would need to be verified and accepted by the engineer of record. Anytime you have openings in your plywood, you should have blocking and edge nailing around the edges of the plywood at the opening. There's another picture with a whole bunch of different holes cut through the plywood. That would need to be verified and accepted by the engineer of record. And as mentioned before, all the openings would need to be blocked around and edge nailed around all of the openings in the plywood. So looking at the nailing of your fasteners of your lateral system plywood, you want to make sure that you got the correct nail size and type. Make sure that the head is flush with the surface and not overdriven. You can overdrive up to 1/16 of an inch. It should have a minimum edge distance of 3/8 of an inch. Galvanized if it's exterior sheathing. Also go around and look at the backside to make sure you don't have any shiners where they miss the frame. Verify you've got the right head diameters on your nails. Also make sure you've got the right nail. The common box or sinker, typically plans are always designed based on common nails, which have the largest diameter. If they're going to substitute any other nails, that would need to be a substitution approved by both the structural engineer of record and DSA. This shear wall is useless when the nails miss all the studs. You can see all the shiners. This is an example of roof boundary and edge nailing. You can see on the right there described different zone nailing, 10D at 2.5, boundaries 10D at 4, other panel edges. The 2.5 applies to not only the boundaries but to continuous panel edges. You've got zone 2, which is nailing at 4 and 6. The bottom picture identifies where the zones 1 and 2 are located on the roof. Next picture shows a little more detail. For roof diaphragms and floor diaphragms, horizontal diaphragms, there are quite often 3 nailing schedules specified. You have the boundary and continuous panel edges, you have other panel edges, and then the field nailing. So this one on the left would be 2.5, 4, and 12. For shear walls, you only have 2 called out, is edge nailing and field nailing. So the edge nailing applies to all edges of all the plywood, and field nailing applies to the middle of the plywood, and then that same edge nailing is applied to all your boundary members, which would be your hold downs, your drags, your sills, top plates, roof level, etc. As far as this one, you'll notice that the continuous panel edges on the left, they show the 2.5 inches on center. You get 2 rows of edge nailing down row 2 because it's the edges of the boundary of the 2 different diaphragms. So you have the 2.5 inches on center on the left and 4 inches on center on the right, all the way along it. If this weren't 2 different diaphragms and this was a shear wall down the middle, as I mentioned before, it's probably the same case. You'd probably have 2 rows of edge nailing because it's considered a diaphragm to the left of the shear wall and a separate diaphragm to the right of the shear wall. So there's a nailing for the left diaphragm and a nailing for the right diaphragm. It should be a red flag to you if you go into a building and you've got a shear wall that runs all the way across the length of the building, and your shear wall has really heavy nailing, and then you go up to the roof and it's just got nailing at 6 inches on center, or they just nailed it with field nailing it in the open panels, in the areas in the middle of the panels. You need about the same number of nails coming out of your roof diaphragm into the shear wall as you are for shear wall nailing. So if your shear wall nailing's at 3 inches on center and your roof diaphragm's 6 and 12, if you had 2 rows of 6 and 12, you end up with about the same 3 inches on center. So it's just something to keep aware of, that you want about the same number of nails in your roof as you've got in your shear wall. Of course, many shear walls are much shorter than the overall diaphragm length, so then you'll have collectors that run all the rest of the way across the roof. Beyond the shear walls, they should be strapped, and then you have the nails into the collector, and the collector then drags into the shear wall, which then has the heavier nailing. It's just a picture showing that at your edge nailing, your plywood, you've got blocking that's supposed to be required there. Obviously missing the blocking, so you've got shiners. So for top plate splices, you can see the heavy line in the bottom plate and the top plate showing everywhere there's a splice. And each place between the splice, you should have the top plate splice nailing in the schedule. Should be somewhere on the drawings. Obviously this one is missing the splice nailing between these two locations. It's got to be between every time there's a break in the top and every time there's a break in the bottom. As you can see, without the appropriate nailing on every splice, it just pulls apart. This detail shows a typical collector might be interrupted by a beam. Shown as a double top plate, could be a beam or some other collector. So whenever it's interrupted, your collector must be tied across the beam. They've shown a couple hold downs across the beam where it gets interrupted. The collector's got to work in both tension and compression. It's got to work both ways. So right now there's a gap shown in this drawing. You cannot have a gap because otherwise you won't be able to transfer your compression loads when the top plates or the collector goes into compression. This is a picture of a top plate splice that's got a bolted plate splice. As you can see that the edge distance of the bolt to the end of that plate is getting very close. There's always a 7 diameter end distance for bolts. This picture shows an offset in a strap. If you have a large offset in a strap, you don't want to take the strap and bend it sharp down to the lower recessed area. When the strap is loaded in tension, it'll just straighten out. You want to try to transition that strap from the higher area to the lower area with a long gradual length. If it's a large offset, you'd want to get a detail from the structural engineer as to how long and how to detail it and how to connect how many nails in the furring member or the tapered member to the other beams. But generally all straps should be in the same plane all the way along the length of the strap.